discussing. So shall I start, Bhankata? Sorry, I wait for you. I mean, yeah.
No, no, it's
Bhankata,
okay. Yeah, you please just start. Yeah, I think there's no formality. Yeah.
yeah, okay,
Okay.
fine. Yeah.
Please go ahead.
So yesterday we started this. Sorry, this touch screen thing is sometimes. Yeah. So we started discussing hyperbolic plane geometry, and we learned about we have already learned about different models, and then I ended yesterday with this theorem that you take any discrete subgroup of PSL2R, then the discreteness is essentially equivalent to whether the group gamma acts properly discontinuously properly discontinuously on the apparat space. All right. So we will start from here today, and uh, uh, so where we want to use it. So that's the question, and that's what I will address today. So you see, the aim of my these lectures is to give you a quick introduction to the Teichmuller space, right? But so far I have not spoken anything about the Teichmuller space. So today, what I will do, this is 8. So okay, so I will give you a basic introduction to surfaces and Teichmuller space. Okay, so this will be a quick introduction, which will help you in appreciating the two talks that Jayadev Atreya is giving next week. And also, it will Somo's lecture will complement whatever I am going to speak now. Okay, so we will start with, we start with a piece of paper. Okay, it's like that, right? I mean, the paper we write, piece of paper. Uh, and what we would like to do, we would like to glue these sides. So you first you take a glue and glue these two sides. What you will get is a cylinder, right? So this is a cylinder. Okay, so this is homeomorphic to S1 cross R. And then what you do, you glue this these two sides. Okay, in a manner so that this point is glued to that point, that to that, and so on and so forth. So we call it gluing in a orientation preserving way. So that means whatever vertical line, when I'm joining one point to the other using a vertical line, I am just gluing in a manner. I'm just gluing in a manner that these opposite points are glued to each other. The same way we glued these two sides also. Okay, so if you glue these two circles in a manner like, like you have this cylinder and you glue this circle with that circle. Okay, so what you do, you just fold it in a way, something like this. Okay, it's a bad picture, but anyway, so you fold it in a way and you glue them together. Okay, so that will give you a object which we call a torus. Okay, torus. So it is like is a, is like tire of a car, or those who are, I mean, now we are in a open world, right? So I mean, if you happen to stay in a metro city or moderate uh, city, then there is a these days there is a thing which is very popular among children. It's called donut. Okay, so it's called donut. right? So this is a donut shaped surface. So it's like a donut. So you know, donuts looks like this, all right? And you, this portion is filled with chocolates and sprinkles, etc. But the surface that is obtained in this way, you start with a piece of rectangular strip, and then you glue the opposite sides. Then you get a donut shaped space, which is called torus. All right. So this is the example of a surface. Okay. And then also we have our surfaces, like sphere is a surface. Okay. So you can also do the following construction. So you take two torus like this. Okay. Then what you do, you remove a small circle, a small disc from each of these torus. You think of them as you are biting at this point, and there is a round hole. Now you glue these two boundary circles of these holes the same way, like you map the, you know, if you join them by a cylinder, the way you glue with one circle to the other while gluing a cylinder to get a torus, you glue in a similar way. Okay, so that will give you a surface like this, like, you know, those mumpali surf, right? I mean, you have mumpalis, but where, you know, those mumpalis without peeling of the cover. So it looks like that, but there are two holes here. Okay, like this. So this is called a surface of genus 2. Okay, and you continue the procedure. Okay, so continuing this gluing process, one obtains surfaces of G number of holes. Okay, and that is called surface of genus G. So you have, so this is something like, so this is a surface of genus 3. Okay, so I call it sigma 2 and I call it sigma 3. Okay, a connected, compact, orientable surface of genus G. All right. So this gives you a construction of constructing a surface by just cutting and pasting papers. Now, compact, all of us know that the surface are closed, and you can think of them as bounded in R3, so they are compact. Orientable means, you know, I mean, if someone is traveling along these surfaces, they will not lose the direction. They will not lost. They will not be lost. Okay. And connected means topologically connected. Everyone knows. Now here is an example of a non-orientable surface. So there are non-orientable surface. I don't want to get into the detail because this is just a talk of about 1 hour. So non-orientable surface, how do you get? You start with the same rectangular strip, okay, and then you glue this side with this side in a opposite or orientation reversing manner. That means what you do, you take this point A, this corner A, you are gluing with this corner, and then you glue this corner with that corner. Okay, so call it A1, A1. Okay, so in this way, what and similarly for all this point, so this orange point you glue with the symmetric orange point here, and this purple point here, you glue with this. So in this way, in a orientation reversing way, you glue them. What you get is a surface which you can actually try to construct this surface using a piece of paper when you are at laser. It's called a something like this. Okay, so this is the surface. Okay, so this is called a, uh Mobius band. So this is an example of a non-orientable surface. So this is one example. There is one more example that also I would like to note here. So you just take the sphere S2. So this is a compact orientable surface, okay? But what I am doing, you take S2 and you glue points which are diametrically opposite. That means S2 with antipodal identification. Okay, so this will give you one surface. Okay, so it's called, so if you do that, then what you get the upper hemisphere. So the lower hemisphere map, the lower hemisphere, you can just cut the so if you assume that this point and this point are same, you can cut this ball, or the surface S2 by a scissor. What is left with you is this upper hemisphere along with this boundary circle. But there you have this opposite orientation. All right, so this point is mapping with, so let me change color so that it will be more visible. So this will identify with this somewhere, and this will identify with this somewhere, right? So this space, this is an example of a non-orientable surface, is called RP2, the real projective space. All right. Now, one way, I mean, you can easily see that these are examples of non-orientable surfaces, because suppose you start walking on the Mobius band. Okay. Uh, so I mean, there are lots of YouTube videos where you can actually see a person when he starts walking along here. When he will cross it somewhere, he will found himself in a way which is opposite to uh, his original orientation. So so that means these surfaces are non-orientable surfaces, and you cannot actually preserve a orientation in a nice way with them. All right. Uh, so these are example of non-orientable surfaces. Since I am just give me 1 minute. So, hello. Ah. Yeah, sorry, there was a phone call. All right, so we were here. Okay, so this is RP2, and these are non-orientable surfaces. Now, what I want to state here is so more formally, let me define at least what is a surface. So definition. a surface is a connected, okay, surface is a topological surface is a topological space. You can assume house drop, second countable, that locally looks like R2. That means you look at these surfaces, you take any point, okay? Then around every point, you always get a small neighborhood, which is a open disk. So this locally looks like R2, and you can do it everywhere. All right. And this is also not very difficult to prove using that cutting pasting method. Okay. And actually, you can also find a smooth chart. So you can also find around every point on the surface. Okay, so these are sort of this is intuitive description of surfaces. I have already told you how surfaces can be glued to each other. Now, the starting point for us here is the following classification of surfaces. Okay, so theorem is a very classification theorem. So this theorem says that every compact connected oriented surface is homeomorphic to one of okay R2, S2, or sigma G. All right. So you take any compact connected oriented surface, then up to topological homeomorphism, these will be either of these types. So there are only up to homeomorphism, there are only countably many of such surfaces. All right. So
So
this is
Sindhu, because it is compact, maybe you can remove this R2.
R2. Sorry. Yeah,
Yeah,
absolutely.
yeah,
Sorry. Thank you.
yeah, and
Yeah.
also you can maybe you can say it is a compact without boundary.
Yeah,
Yeah,
absolutely. Yeah.
yeah, yeah, yeah,
Compact without
yeah,
boundary. Yeah, thanks.
yeah.
So since this is the case, then actually I can write to sigma g where g greater than equal to 0. So sigma 0 is S2. All right. So so this is the classification theorem, and this is the starting point for us to get into this uh, Teismuller theory. Okay, so this is one thing that we would like to know. The second thing is the concept of fundamental group of a topological space. Okay, so actually what we really need. Okay, so let me not get into that. Okay, so to each surface sigma g, one can associate a group called the fundamental group of a surface. Okay. Now, two surfaces are homeomorphic. So, two surfaces are homeomorphic if only if their fundamental groups are isomorphic. Now we have already seen that we have a topological classification of surfaces. All right. So that means we also have a isomorphic classification for the fundamental group of a surface. Okay. So here is the result that I just write down. Okay. So let phi1 sigma g fundamental group of sigma g. So then phi1 s2, that is identity, and phi1 sigma g is a group that is generated by 2G generator, and they satisfy one single relation. Okay, so okay, so this is the fundamental group of a surface. Okay, so topologically this is actually the space of so topologically phi1 of x is the group of homotopy classes of oriented loops based at a point x. So here, so here my surface, I would say a surface here, because normally one assumes some sort of path connectivity while defining it, but for us this is just this. Okay, so this is the object that we need, the fundamental group of a surface. Now if you don't know this meaning of this group presentation here, so it means this group is generated by 2G elements, which one denotes by A1, B1 up to AG, BG, and those 2G elements generate the whole group, and they among themselves they satisfy this relation that product of their commutator is equal to 1. Okay, so you can think of it as a finitely generated group by 2G generators satisfying this single relation, where generators satisfy this single relation. Okay, so this is one thing that we would actually be needed in order to define what is Teichmuller space. Okay, so now yesterday we observed that a group acts freely and properly discontinuously is equivalent to the fact that the group is discrete. And then the last assertion was that the map from H2 to H2 mod gamma is a covering space. So maybe I just recall what is a covering space also. Recall, okay. So let X be a topological space, a covering map, okay, covering map is a topological space Y along, okay, not a covering map, it's a covering space, along with a, okay, I call it x tilde, okay, not x tilde, let me call it x hat, along with a surjective continuous map. So you have xt to x, and these are the following property, that for every point x in x, okay, there exists a open neighborhood ux such that P inverse ux is a disjoint union of open sets in C. Okay, so P V B V I, where lambda is some index set, and P restricted to each of the Vi is a homeomorphism. So that means corresponding to this, you have several pre-images, homeomorphic pre-images of this neighborhood Ux. Okay, so this is covering space, and a covering space x tilde of x is called a universal cover if x tilde is such that every loop is, every loop, not is, every loop can be shrinked to a point. Okay, that is the fundamental group of x tilde is identity. So a simply connected cover of x is called an universal cover of x. All right, and as you can see from this definition, that the fundamental group of a topological space is closely related to the theory of covering transformations or covering space. Okay, and now the covering map I mentioned yesterday, that is uh, coming from this group action, where, okay, so yesterday's covering, okay, so yesterday's covering, you have H2 and you have H2 mod gamma, right? So this is the set, this is called gamma x, such that x in H2. So right, that when you have a group action, either two orbits are equal or they are disjoint. Now consider the set of all orbits under gamma action. Okay, that you can give a topological structure, and there is a natural map from H2 x to gamma x. There is a natural surjective map. So yesterday's result says that this surjective map is actually a covering map. All right. So and H2, you can see that's a disk. So you take any loop. Okay, you can think of uh, the loop, the loop is the region that the loop bounds, that there is no gap or there is no hole inside that, right? So you can shrink it to a point. So that means the fundamental group of H2 is also identity. Okay, uh, so this means that whenever you have any space like H2 mod gamma, H2 you have a unit. So given, so this means given any Fuchsian group gamma, I assume it is torsion free, then the space H2 mod gamma as H2 as its universal cover. And H2 mod gamma, this is a surface. Okay. So H2 mod gamma is a compact connected surface. So it is homeomorphic to one of the types that I have already mentioned. Okay. And this gives us the concept of a hyperbolic structure. All right. So I will quickly recall. So what is a hyperbolic structure? In fact, I will make a more general definition. Okay. So definition, geometric structure. Okay. So let me define what is a geometric structure. Okay. Okay. So let X to be either E2, H2, or S2. Okay. So let S be a topological surface. A geometric structure on S consists of an open cover of S and a collection of maps okay phi I ui to X such that phi I ui to phi I ui is a homeomorphism for each I, and if you have non-empty intersection among these open sets, then the transition maps phi I compose phi j inverse this is restriction of an orientation. Why orientation preserving? This is restriction of an isometry of x on each connected component of phi j ui intersection ej. All right. So usually we will take orientation preserving isometry. Okay. So uh, restriction of an okay. All right. So this is the definition. Maybe I should say here that so for the moment I take orientation preserving isometry. Okay. So we will assume the isometry. Okay, so that means what is the same like your definition that you might have seen in manifold theory, right? So you have a space ui, and this is mapping onto a onto some vi, and you have uj. Okay, not here. You have uj. Okay. Oops. You have uj. Okay, that is mapping onto some vj. Then this portion is mapped on the shaded portion, and on the shaded portion this is phi I, this is phi j. On the shaded portion, this transition map phi I compose phi j inverse. Okay, that is restriction of an element from the isometry group. Okay.
Uh,
Yeah.
Krishnamurtha,
Yeah.
why do we need this connected, so on each connected component of 5G of this thing? Why are we saying this? Like,
Because if it is, I mean, what I really mean that, yeah, so uh, it's not needed, you're right. Okay. But the point is that this phi j ui intersection uj, this may not be uh,
connected,
connected. So that means
then
on each component, you are it is induced by isometry. That's what I mean. Okay.
but why not on the whole thing? Like, even if it is disconnected, isometry makes sense, right? Restriction of isometry makes sense.
Even it is, yeah, I think the same definition. Yeah, I mean, of course, I mean, what you were saying is true that if it is not connected, even then you can say that it's a restriction of an isometry. There is no problem. Okay.
Okay.
Yeah, but when you say connected component, that means you just want to somehow emphasize that emphasize the fact that the space in general and this image of ui intersection uj may not be connected, right? So it may have different components, and on each component it is induced by some isometry. It may happen that on different connected component the isometry is different. It can happen, right? So it may not be a single isometry that works for all the connected component. Uh, it may be different isometries. Yeah.
Okay. All right. Yeah.
Right. Yeah. Okay. So that's why I mentioned that this is connected component. Okay, so this is a part of a very more general definition. So actually you can define similar geometric structure for any topological any manifold x and any Lie group acting on x. All right. Uh, but here we will restrict ourselves only to this setup. Okay. So now, what are good example of such geometric structure? So one example is given by the covering space. Okay. So I hope the definition is clear, right? So let me just note down. Okay. So when X is H2, then the geometric structure on S is called a hyperbolic structure. If X is S2, then spherical structure X is E2, then Euclidean structure, or sometimes it is called affine Euclidean structure. All right. Okay. So this is just a brief comment. Okay. So now what I say that suppose S is equipped with a geometric structure, then any cover of S can also be equipped with the same structure. Okay, with a natural geometric structure. Okay, so let me, since we are talking about hyperbolic structure, let me just call it hyperbolic. Okay.
So, Krishnendu, is there any relation with this projective structure?
A projective structure means these transition maps come from a different group. So here we are not talking about that. So
Okay,
projective structure means your underlying this space X that we started with, that will be the real projective space, and the group will be the general linear group. Yeah, but in dimension two, I mean, if you replace X by say complex one-dimensional complex projective space, right, which is a sphere, and the group as SL2C, then that gives you one-dimensional projective structure on a surface. But here I am not talking about projective structure.
Yeah,
Actually.
okay. Yeah.
Yeah, because that's why I only assume. I mean, I assume that this X is one of these, and the restriction maps are the isometries. Okay. Yeah, so I assume that. So now I will write one theorem, which I would not be able to prove, of course, but this essentially gives you that most of uh, our surfaces are uh, modeled on the hyperbolic space. Okay, so let S be a connected surface equipped with a hyperbolic structure. Okay. And assume that the natural path metric on S is complete. Then S is isometric to H2 mod gamma. Okay. Where gamma is a discrete torsion free group. Okay. So that means you take any surface plane is universal. Okay. So this is essentially this theorem is saying. Okay, and it is also known from a result in Riemannian geometry that in dimension 2 that there can be at most 3 simply connected, complete path connected Riemannian metric space, either the Euclidean plane or the sphere or the hyperbolic plane. Okay, so but this theorem essentially giving you that all the surfaces where one can give hyperbolic structure is modeled on the hyperbolic plane. Okay, and then you have the uniformization theorem that further tells you that most of the surface. So let me just write it down. So any surface sigma g where g greater than equal to 2 has H2 as its universal cover. This is the uniformization theorem, all right? So uniformization theorem. Okay, so that means you take, so the punchline is the following. Since I am running out of time, I want to finish it quickly because I want to define what is the Tate-Muller space. So let me just write down. So punchline, maybe another theorem. Let X be a surface with a complete hyperbolic structure. Okay. Then X tilde, the universal cover of X is isometric to H2. So this is what? Okay. All right. So now corresponding to every geometric structure, you have 2 natural maps. So one map is called a developing map and the other is called a holonomy map. So let me just quickly tell you. So X hyperbolic surface, all right? So then you start from a point on the hyperbolic surface, say x naught, okay, x naught, and then you draw it, you join it by a path, say x1. Okay, so what you can do here, Okay, so what, let me just, maybe I define it quickly. Okay, so, okay, so let me, uh, so let me not, how to define it in a short time, just give me some time. So let me write down a comment here. Okay, so to each hyperbolic structure, there is a, okay, so sorry. So let start with a hyperbolic surface. So let X hyperbolic surface. Then you have a coordinate atlas. I mean coordinate charts as defined. Now these coordinate charts, okay. So also let x tilde to x p is the universal cover of X. Okay, so then there is a map. Then there exists a unique, in some sense. Okay, so there exists a unique map. I would not call it a unique, but so there exists a well-defined map dev from x tilde to h2 that globalizes the coordinate charts. Okay, so there is a developing map. I am not defining what is a developing map, and okay, so there is a developing map and a homomorphism, which is called holonomy, from the fundamental group of the surface to PSL2R. Holonomy representation. All right. Now the holonomy and the developing map, they characterize the hyperbolic structure. Okay. So the pair dev hole characterizes the hyperbolic structure. Okay. And one can also prove that the holonomy map is actually injective for a hyperbolic surface. Okay, so if you have a complete hyperbolic structure, then the holonomy map is injective. Okay, so
how it is defined, Krishnendu?
yeah, so
It
that's
just
what I am wondering whether I should
okay.
say it. Maybe because if I say that, then maybe I will say it. All right, just give me
Mhm.
1 minute.
Yeah.
So let me give you how the holonomy map is defined. Okay, okay. So So what you do, so we will assume for the moment that you take a, you know, you go to X tilde, all right. So let X tilde universal cover of X. Okay. Then X tilde is also a hyperbolic surface that is simply connected. Okay. So now, this is a path connected space, right? So what you do, you choose a base point, choose a base point x naught in X tilde. Okay, so I have this base point x naught. Okay, and then what you do, you choose a path from x naught to a point x1 in X tilde. Okay, now corresponding to x naught, you get a coordinate chart which is denoted by u1. Okay, and then this whole path you can cover by coordinate patch like this. Okay, so these are all my coordinate patches. Okay, now we know that if you have a coordinate chart from ui to h2, okay, that agrees with some element in PSL2R on this intersection. Okay. Now there is also a sort of unique extension property. Okay, so what you can do, so let me write it down. So cover gamma 0, 1 to X tilde by coordinate charts. As shown in the picture. Okay. Now you see this is a connected space. All right. So what you can do, you can define that so you call it u0, you call it u1. Okay, so note that phi naught compose phi 1 inverse restricted to u0 intersection e1. That is some element g0 in PSL2R. G0, where G0 belongs to PSL2R. Okay, now you define developing map to maybe u0 intersection this gamma to be phi naught u0 intersection gamma, developing map u1 intersection gamma equal to, okay, you call it G1, perhaps that's better. I call it G1. Then you define it to be G1 compose phi 1 intersection E1 intersection gamma. So and you continue this process. Okay, you repeat this process. So then what happened? When you end here, you have defined the developing map throughout the whole path. All right. So define developing map restricted to UN intersection gamma is G1, G2, Gn, compose phi n intersection UN intersection gamma. Okay. So this means developing map is well defined on the whole of gamma. All right. Now you can define developing map of gamma to be the image of this developing map at gamma 1, which is this G1 up to Gn compose phi n at gamma 1. Okay. Now, it might sound to you that developing map at not gamma, yeah, so this is fine, right? Define, okay, just a minute. Define developing map at gamma 1 to be G1 Gn phi n gamma 1. Okay. So this gives you the develop. So this gives the concept of the, not concept, this gives the definition of the developing map x tilde to H2. Okay. Okay, so this is the definition, and one can show that this is well defined, and this does not depend on the choices that we have chosen. Okay. Now, as soon as you have a surface X, then you have a universal cover X tilde. Then what happened that you have a concept of you have the definition of developing map from X tilde to H2. And we know that in covering space theory, when you have any map from the universal cover to a simply connected space, you can think of it by lifting properties that it induces a map from X to H2 as well. And that gives you the developing map for a non-simply connected manifold. All right. So this gives you the construction of developing map, yeah, so this gives you the construction of a developing map. And along the process, you can also see that if you replace this path instead of x0 to x1, if you consider this as a path which is a loop on based at x0 itself, then the same construction will give you a representation of, it's not P, it's x0. So give a representation, oops. Okay, so some problem. It gives you a representation of pi 1 x0 to PSL2R, which is the holonomy representation. All right. So this is how developing map and holonomy maps are constructed. So corresponding to hyperbolic structures, you have this. So given a hyperbolic structure, there exists a faithful discrete representation from sigma hyperbolic structure on xp to PSL2R. Okay, so now definition. So let sigma g, okay, you can take g greater than or equal to 2 be a compact connected oriented surface of genus G. Okay. Now you fix this surface. Now on the surface, fixing this surface, you can give all sorts of hyperbolic structure in the way I have described. And for each hyperbolic structure, you get a representation of this type. All right. So the Teichmuller space of genus G is defined as, I am changing notation, so this is maybe I call it S. Okay, so this is, this is discrete faithful representation of PSL2R modulo conjugacy. Okay, so the genus G is the set of discrete faithful representations of pi1s into PSL2R up to conjugation. Okay, so this is called this is called the Teichmuller space of a surface group or of a surface. All right. Now you can see that this space, Teichmuller space, comes as a quotient of PSL2RG, right? So this gives quotient. Okay, so this gives a natural topology on tau s. Okay, and it's a result that I don't think I have much time to prove, but it's a theorem that the Teichmuller space is homeomorphic to or 6G minus 6. Okay, so where I have assumed G is greater than or equal to 2. Okay, all right, so this is the result. Now there is one more description of the Teichmuller space that I will quickly tell you. Okay, so there is one more description. So definition 2. Okay, let S equal to SG. Okay, then Teichmuller space is the set of all equivalence class of where X is a hyperbolic structure on S, F S2 X is a homeomorphism called marking, and XF is equivalent to YG if and only if there exists an isometry F, okay, not F, there exists an isometry alpha from X to Y such that alpha compose F is homotopic to G. Okay, so this is the second definition. Now these two definitions are equivalent. Okay, so it's a fact that the two definitions are equivalent. Okay, now finally I would like to mention that another definition, that there is a group that one can define. So the group is, you take the set of all orientation preserving homeomorphisms, okay, and then let me write down. So homeo plus S is the group of all orientation preserving homeomorphisms of S, okay, and homeo not S is the connected, okay, is the connected component, that's fine. Is the connected component of homeo plus S that contains the identity. So this group is called the mapping class group of S. Okay, and this group naturally acts on the Teichmuller space. Okay, so you know, because so given phi in the mapping class group, and you take a point in Teichmuller space. Just a good minute. Hello? हाँ वो बाहर रख दीजिए, ठीक है? ये yeah, hello?
Yeah.
Yeah, so you have phi in mod S and xf in the Teichmuller space, okay? Then there is a natural action of phi on the point on the Teichmuller space as x, and then you have what? You have f compose psi inverse. Okay, here psi is a representation, representative. Okay, representative of phi. Okay, so this gives a natural action of mod s on the Teichmuller space, and I would finish by setting a result. I do not know whether Somo. I think Somo might discuss this again. Okay, all these what I have said. I think I would request Somo to. Somo, you will discuss, no?
Yeah, yeah, yeah.
Yeah. Mod s acts on Teichmuller space properly discontinuously. I think I will stop here. Yeah. So this is a vast. You need. I mean, in 2 lectures. I mean, it was a challenging task to
Yeah, 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 yeah,
so much
definitely.
material.
Yeah, definitely. Yeah.
Yeah, yeah.
So
So,
maybe yeah. So maybe Soumya give some examples also, and we'll explain next.
yeah, yeah. Soma will focus on mapping class group, and
Yeah.
he may discuss the proof of this theorem, and he may define the Teichmuller space again, right?
Yeah,
And
yeah, definitely. Yeah, yeah,
okay.
yeah. Because some of us actually have seen first time, so it's
Oh, I see. I see. So Soma, you can repeat. Actually,
yeah,
Soma
yeah,
then. I mean, if
yeah,
needed, I think Sunday also Soma can give one extra lecture.
yeah, yeah. No, yes, yes, yeah. Of course, yeah. It's completely informal discussion. It's
Yeah,
not
yeah,
actually.
exactly.
Yeah, yeah. It's
Yeah.
nothing is because we have to achieve this thing. We have to finish this thing.
Yeah,
No, no.
yeah, yeah.
I
No,
think
I
not.
plan that I will
Yeah.
give you the proof of this
Mm-hmm.
development holonomic theorem, and
Mm-hmm.
the result that every simply connected hyperbolic surface is homeomorphic to isometric to H2.
Mm-hmm.
Okay, but I think it is not possible in a short span of time with
So,
uh,
but
with
if you have some, but if you have some notes regarding this, maybe you can
yeah,
share.
so I would recommend everyone to look at this book. So there is a book by Bruno Martelli.
Mm-hmm.
Okay, so this is a very nice book,
Yeah.
okay, and very self-content book is by Bruno Martelli called Geometric Topology. I wrote it. Okay.
Yeah. Yeah.
If anyone who is interested in building a prerequisite for next year's program by Banktes
Yeah.
and
Yeah.
others, they can read this book. I mean that covers plenty of basic material.
Yeah. 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 Okay.
Yeah,
Yeah. Okay. So, thank you, Krishnendu, for
yeah,
this nice talk, and maybe we'll discuss more in this Somya talks
yeah, yeah, yeah.
tomorrow, the day
Absolutely,
after tomorrow. Yeah.
absolutely. Now tomorrow, right? So we are
Yeah. Yeah.
giving.
Tomorrow. I think. Yeah. So there is an announcement that tomorrow talk will be at 5 p.m. Is it? I'm correct.
Yeah,
Yeah,
yeah, yeah.
because tomorrow is 9th, so you told me that
Ah,
9th you fixed on 5th.
right, right, right.
So tomorrow talk will be at 5 p.m.